Hi, I'm Eliad Tsfadia. This is a joint work with Iftach, Haitner, Noam, Mazor, and Silbak on the complexity of two-party differential privacy. We first start by describing what is differential privacy. In differential privacy, the setting is that we have a mechanism M that gets as input a database X that contains sensitive information of individuals. Usually, the goal is to compute some global statistics over the database without revealing information about any single individual. Informally, we say that M is differentially private if one record does not change the output distribution too much. This means that if we look on a different execution, where we change one of the records, for example, in X prime, we replace X2 with X2 prime, then the output distributions MX and MX prime should be almost indistinguishable. In order to see why this gives us privacy, think of X2 as the sensitive information of Alice. So for example, in X, Alice participates, and in X prime, Alice does not participate or provide fake info. Given the guarantee that the outputs of both cases are almost indistinguishable, means that the output of M does not reveal almost any information about Alice or any other single individual. Such databases, X and X prime, that differ on a single record are called neighboring databases. Note that we cannot hope to compute something meaningful while guaranteeing that MX is exactly equal to MX prime for every neighboring X and X prime, because this basically means that the output of M is independent of the input database. So we must allow some indistinguishability loss. Usually, this loss is captured by epsilon delta parameters. Formally, we say that M is epsilon delta differentially private if for every neighboring databases X and X prime and every event H over the outputs, the probability that MX is in H is epsilon delta close to the probability that MX prime is in H. As an example, suppose that Tel Aviv University wants to publish a differentially private statistic about its workers, like the number of workers that suffer from high blood pressure. Let X be the binary database, where Xi is 1 if the ith individual suffers from a high blood pressure. So we are interested in the sum of the Xi's. The common way to privately estimate it is by adding noise to the sum that will mask the influence of a single record. And the most common noise that gives epsilon differential privacy is the Laplace noise of magnitude 1 over epsilon. What we have described now is called the centralized model. The mechanism M has access to the entire database X, and the goal is to estimate some function f on X while preserving privacy. The focus of this talk is on a different model called the distributed model, and in particular, the two-party case that we will describe in the next slide. So what is two-party differential privacy? In this setting, we have two servers, A and B. Server A holds a database X, and server B holds a database Y. They interact with each other according to some protocol pi in order to estimate some function f over the joint data X and Y. So the goal is to estimate fxy while preserving epsilon delta differential privacy. This means that in order to protect the privacy of B, we require that for every database X and every neighboring databases Y and Y prime, the view of A in the execution pi xy is epsilon delta indistinguishable from the view of A in the execution of pi xy prime, where the view of A is whatever A learns from the interaction without loss of generality, its input, private coins, and the transcript of the execution. Similarly, in order to protect the privacy of A, we require the same thing with respect to the view of B. In this work, we are interested in understanding how hard it is to construct two-party DP protocol compared to the centralized model in which a single server holds the entire data. For some functions, the task is basically not harder than doing it in the centralized model. For instance, suppose that again Tel Aviv University wants to privately publish the number of workers that suffer from high blood pressure. But the situation now is that there are two different faculties, each has data for its workers, and each faculty wants to protect the privacy of its workers from the eyes of the other faculty. Still, at least for this case, it is easy as in the centralized model, since the first faculty can privately estimate the sum of the xi's by adding noise, and the second faculty can add noise to the sum of the yi's, and the output will be just the sum of those two estimations. Using similar constructions, it can be shown that the task is as easy as in the centralized model for any modular function that can be written as the sum of f1x plus f2y. However, the task seems much harder in the general case, for example, when fxy is the inner product between x and y. The inner product is one of the most fundamental two-party functionalities because it measures correlation between databases. In order to emphasize its importance, think, for example, that A holds a database X that contains information of who is a smoker and who is not in a group of people. Say 1 indicates a smoker and -1 means not a smoker. And B holds a database Y of the high blood pressure information about those people. So in order to learn whether there is a correlation between smoking and high blood pressure, the parties wish to exactly estimate the inner product of X and Y. Yet, they want to do it while protecting the sensitive information of each server from the eyes of the other server. Regarding upper bounds of DPIP, inner product, it turns out that there is a way to privately estimate the inner product using a randomized response, where A sends a noisy version of HXI, and B estimates the inner product based on it. This approach leads to an additive error of square root of n over epsilon for every xy. If we would like to achieve accuracy only for uniformly random databases x and y and not for every xy, then the parties can simply output 0 without any interaction. This will give us an additive error of square root of n just by the properties of the binomial distribution. Yet, note that in the centralized model, where a server holds both x and y, it can achieve an error of only 1 over epsilon for every database's xy and not just random ones by simply computing the inner product and adding Laplace noise. Namely, there is a large gap between the two-party and the centralized model with respect to the inner product functionality. This leads to the following natural question of, is there a more accurate two-party DP-IP protocol? It turns out that the answer is no. There is a lower bound by McGregor et al., which states that for every epsilon delta DP protocol pi, the additive error on random databases must be at least square root of n over log n. Namely, up to the log n factor, the trivial protocol that the parties output 0 is the best thing we can do. This led researchers to think about a relaxation of differential privacy called computational differential privacy. Here is an equivalent definition of standard DP that we saw in the first slide. So M is epsilon delta DP if for every neighboring databases X and X prime and every unbounded distinguisher D, the probability that DMX is 1 is epsilon delta close to the probability that DMX prime is 1. Now, using this view of the definition, we can naturally define a computational relaxation of it called epsilon delta CDP, where we require that the above only holds for polynomial time D and not for every unbounded D. Namely, an unbounded D might be able to distinguish between the MX and MX prime, but an efficient D cannot. We denote this relaxation by superscript C. So in two-party CDP, our relaxed goal now is to estimate fxy while only preserving epsilon delta CDP, computational differential privacy, meaning that the views on neighboring executions should only be computationally indistinguishable. It turns out that with the CDP relaxation, we can close the gap between the distributed and the centralized models under cryptographic assumptions. Namely, the parties can simply simulate a centralized mechanism M using secure multi-party computation, and the output of the protocol will be just the output of the simulated M. Using this scheme, it follows that if M is a centralized epsilon delta DP, then the protocol pi is epsilon delta CDP. Secure MPC is done using oblivious transfer, which is a standard public key cryptographic primitive. So in our case that we are interested in estimating the inner product, the parties can simply simulate the centralized mechanism M that just adds Laplace noise. So we saw that using oblivious transfer, we can construct accurate CDP protocols because we can simulate any centralized mechanism. This leads to the following main questions. What is the minimal complexity assumption needed to separate between distributed DP and CDP? In particular, are one-way functions, the most fundamental cryptographic primitives, sufficient? Or is public key cryptography necessary? And actually, even if public key crypto is necessary, it is interesting to understand whether we have to use generic MPC for constructing distributed CDP. MPC is expensive in many cases and require many OT calls, not just a single one, so it is usually highly impractical. Here's the picture of the complexity hierarchy. The lower part is the secret key crypto world, where we have one-way functions, which are the most basic cryptographic primitives. This world is well understood since other primitives like pseudo-random generators, pseudo-random functions, commitments, and so forth are known to be equivalent to one-way functions. The higher part is the public key crypto world, where much less is known. The most fundamental primitives of this world are key agreement and the oblivious transfer. Our goal is to understand what is the place of non-trivial distributed CDP. Namely, what is the complexity of a two-party computational DP protocol, which has accuracy that is impossible to achieve with standard DP. First, as we mentioned, it can be done using OT via secure multi-party computation. Second, when the non-trivial accuracy is obtained for a noticeable part of the inputs, it is also easy to show that such a protocol implies the existence of one-way functions. Previous results have made progress on understanding this question with respect to Boolean functionalities, where each database only contains a single bit. They show that non-trivial CDP protocol for estimating the XOR of the two bits requires the existence of oblivious transfer. However, Boolean functionalities, and in particular XOR, are less interesting in the context of DP, since even in the centralized model, the error of a DP algorithm for estimating the XOR must be close to half. In contrast, the inner product, which is a much more natural functionality on large databases, has much larger gap between the possible accuracy in the two-party DP and CDP. So in this work, we focus on understanding what is the place of CDP protocol that has non-trivial accuracy in estimating the inner product. First, as we mentioned, it can be done using OT via secure multi-party computation. Second, there is a result by Haitner et al., which shows that it cannot be done in the random oracle model, and thus using black box access to one-way functions. Our result is that non-trivial CDP IP implies key agreement, meaning that the place of this primitive is the public key crypto world. We now formally state our main result. Theorem 1, any epsilon delta CDP two-party protocol pi that for some additive error L satisfies that the confidence of this additive error on a uniformly random X and Y is sufficiently larger than L over square root of N. There is a hidden constant here, say a million. So any such protocol can be used to construct key agreement. For example, let's focus on the case where epsilon is a constant and L is a square root of N over C for large constant C. Applying the theorem on the case yields that a CDP protocol that has additive error square root of N over C, even with only 0.01 confidence over random databases, can be used to construct key agreement. Note that this theorem is tied up to a constant, since the trivial protocol that both parties just output 0 is with probability L over square root of n at distance at most L for every L, just by the properties of the binomial distribution. Moreover, theorem 1 also reproves the impossibility result of McGregor et al. In the information theoretic case, and it even has log n improvement in the additive error. In order to see it, assume there is an information theoretic DP protocol with non-trivial accuracy, then theorem 1 implies that it can be used to construct information theoretic key agreement. Since the latter does not exist, we conclude that such DP protocol does not exist either. Before introducing the reduction, we first sketch the proof steps of McGregor et al., and then explain why their arguments in the information theoretic case do not follow for the computational case as well. So let pi be an epsilon DP protocol, let xy be uniformly random databases, and let t be the transcript of the execution. First, condition on the transcript, x and y are independent. This is true for every protocol, not just the DP one. Second, by the DP property, since we started with uniformly random xy, then conditioned on the transcript, both x and y become what is called strong Santavanzirani sources. What is a strong Santavanzirani source? So we say that Z is an alpha strong SV source if for every index I, Zi is unpredictable condition on any fixation of the other coordinates Z minus I. Namely, the probability that Zi equals 1 is alpha close to the probability that Zi equals minus 1. In our case, because the protocol is epsilon dp, we obtain alpha that equals to e to the minus epsilon. Now, McGregor et al. Proved that the inner product is a good extractor for SV sources. Therefore, it follows that condition on the transcript, the inner product of two independent strong SV sources, x and y, is unpredictable, almost uniform modulo square root of n. This completes the proof of their lower bound, since assume for simplicity that the output appears in the transcript, then this output cannot be accurate. So now let's try to understand why the lower bound does not hold for the computational case. Now we have a protocol pi, which is epsilon CDP. As before, let x, y be uniformly random databases and let t be the transcript. Now there are two worlds to consider. In the information theoretic world, it is true that x and y are independent, but they are not strong SV sources since pi is only CDP and not DP. So let's try to understand what happened in the computational world, namely how these sources looks like in the restricted eyes of a PPT observer. By the CDP property, x and y now become computationally strong SV sources, meaning that a PPT distinguisher cannot predict the value of each coordinate given all other coordinates. But the crucial point is that, according to this restricted view, x and y can be very correlated. For example, consider the CDP protocol that both parties securely emulate the centralized mechanism, which simply adds a Laplace noise of 1 over epsilon. From a restricted view of a PPT observer, x and y condition on the transcript looks very correlated because first, the observer knows a good approximation of their inner product. And second, it does not understand anything beyond that by the properties of the secure computation. So our goal is to exploit this computational correlation that we have between x and y for constructing a key agreement. We are now going to see a proof overview of theorem 1, which is done via reduction. We show how to use an accurate CDP IP protocol for constructing a key agreement. Here is the key agreement protocol. The first step is that Alice samples a random database X and Bob samples a random database Y. Now they apply the CDP IP protocol in order to get an estimation out of the inner product of X and Y. Alice then chooses a random string R, sends it to Bob along with XR, which is all the XI's where RI equals 1. Up to rearranging the coordinates, we can think that Alice basically sends the first half of X. Bob then sends y minus r, which is all the yi's where ri equals 0. Namely, up to the rearranging, Bob sends the second half of its database y. Now, Bob can compute the inner product of xr, yr, and Alice can compute the inner product of x minus r, y minus r. Finally, Bob outputs the inner product of xr, yr, and Alice estimates it by computing out minus the inner product of x minus r, y minus r, where out is the estimation of the CDP/IP protocol. Note that if out is exactly equals to the inner product of xy, then out A equals to out B. Now let's analyze this protocol. A key agreement protocol has two properties, agreement and secrecy. For agreement, note that if the output of the CDP/IP protocol is close to the inner product of xy, then out A is close to out B. For secrecy, the goal is to show that the output of any PPTF, given all the information that it sees as an external observer, is far from out B. This information is the transcript T and the strings R, XR, and Y minus R. Intuitively, this should hold since XR condition on the transcript is highly unpredictable by privacy. Namely, it is a computationally strong SV source. Therefore, if the observer OFF only sees this XR and this Y minus R, we somehow want to claim that it cannot predict the inner product of this part and of that part. This, however, is not true in general. For instance, suppose that R is not chosen uniformly at random, but is just fixed to 1 in the first n/2 indices and 0 in the other indices, exactly as in the picture. Now, we cannot claim that F cannot predict the inner product here because we don't know what the CDP/IP protocol reveals in its transcript, in addition to the inner product of XY. For instance, it might also leak a private estimation of the inner product in the first half of the indices. So the protocol can reveal the inner product of XR, YR for a few hours while preserving privacy, but we prove that it cannot do it for many hours, and in particular for a uniformly random R. The proof is not trivial and is done via a new theorem about strong SV sources that we will see in the next slide. We remark that this protocol is not exactly a key agreement, but the gap between the agreement and secrecy can be amplified to fully secure key agreement protocol using standard techniques. So here is our new result about strong SV sources. Theorem 2, if xy is e to the minus epsilon strong SV source, then with high probability over a uniformly random R, the inner product of XR, YR has high mean entropy even when conditioning on R, XR, and Y minus R. Namely, the probability it gets a fixed value is approximately at most 1 over square root of n, which makes it unpredictable. The theorem is stated for information theoretic sources, but it is also holds for the computational case since the proof is constructive. The interesting part of this theorem is that there is high mean entropy even when conditioning on the C-dependent leakage of XR, Y minus R. Note that if we remove Y minus R and even replace XR with the entire X, then the proof simply follows by the extraction result of McGregor et al., since the inner product of XR, YR, when R and X are revealed, is essentially like the inner product of R and Y, which are independent. But when we condition on XR and Y minus R, we cannot write the inner product of XR, YR as an inner product of two independent sources. Therefore, the proof is done by completely different techniques. Again, the proof is constructive, meaning that there exists a PPT rec and some index I, such that for every PPT F that given R, XR, Y minus R predicts the inner product of XR, YR to well, rec given oracle access to F and given X minus I, Y can reconstruct the missing coordinate XI to well. which violates the assumption that XY are a strong SV source. Again, because the proof is constructive, the theorem is also applicable for computational strong SV sources. For summary, first, we saw theorem 1, which states that non-trivial CDP IP implies key agreement, which is our main result. We remark that in the paper, we also provide a much simpler proof for the case that the protocol is promised to be accurate with very high confidence, namely when the confidence of a good accuracy is almost 1 instead of, say, 0.01. Second, we saw theorem 2, which states that the inner product is a leakage-resilient condenser for strong SV sources. We explained that this holds under a C-dependent leakage and using a constructive proof. In addition, in order to prove theorem 2, we had to develop a new self-contained efficient reconstruction attack in the low confidence regime, which can be of independent interest. Regarding open problems. First, it's still left open to characterize the complexity of estimating other functionalities. In this work, we made the first step with respect to the fundamental two-party functionality of the inner product, but providing a more general characterization is still open. Second, it's still left open to understand whether OT is necessary for CDP IP. Actually, our result is tight for a weaker notion of CDP called CDP against external observer, where the indistinguishability only holds with respect to the transcript and not with respect to the view of each party. While our key agreement lower bound also holds for the standard notion of CDP, the upper bound for this case is only OT, which might be the right answer. Thank you for listening.